Symmetry of graphs. A graph can have a line symmetry. That means if it's folded along that line, then two halves will match. Or a graph can have point symmetry, where graph can be rotated 180 degrees with respect to that point and appears unchanged. A relation or function may not have any symmetry at all. So to test for the x-axis symmetry, if we have x-axis symmetry, that means x-axis acts like a mirror for that graph, for that function, for that relation, and replacing y by negative y will produce equivalent equation. So if we replace y by negative y and the equation does not change, that means that equation, a graph of that equation will have x-axis symmetry, and it's actually not going to be a function. If x-axis symmetry, if an equation has x-axis symmetry, for every point xy on the graph, x negative y will also be on the graph. And graph of a relation is symmetric with respect to y-axis if every xy on the graph also means negative xy is on the graph as well, and y-axis will act like a mirror. So test the y-axis symmetry, replace x by negative x, and our equation should not change. If the equation doesn't change, that means we have y-axis symmetry if we replace x by negative x. The graph of a relation is symmetric with respect to origin. If we replace x by negative x and y by negative y and it does not change the equation at all, then we have origin symmetry. So that means every point xy on the graph also means we have negative x, negative y on the graph, and origin is, graph can be rotated about 180 degrees and you get the exact same piece back when you rotate the graph by 180 degrees. That would mean we have origin symmetry. Let's see some examples. Test for symmetry, y equals x squared plus 2. So we want to test this equation for symmetry. For x-axis symmetry, again, the relations will have x-axis symmetry. Relations can have x-axis symmetry, but they would not be functions because they fail the vertical line test if it has an x-axis symmetry. So test the x-axis symmetry, we will replace y by negative y. And if equation does not change, that means we have x-axis symmetry. So let's go ahead and replace y by negative y. Well, it does not give me the same equation, so that means no, we don't have x-axis symmetry. Let's check the y-axis symmetry. To test the y-axis symmetry, replace x by negative x. And that actually does give me the same equation. So we do have y-axis symmetry here. To test the origin symmetry, we replace y by negative y and x by negative x. If equation does not change, that means we do have origin symmetry. In this case, if we replace x by negative x and y by negative y, we actually do not end up with the same equation. So no, we don't have origin symmetry for this problem. We do have y-axis symmetry. We do not have origin or x-axis symmetry. Another example, we want to test this graph for symmetry, x squared plus y to the fourth equals 5. To decide x-axis symmetry, we're going to replace y by negative y. If my equation does not change, that means I have x-axis symmetry. So let's go ahead and replace y by negative y, and we can see the negative to the fourth power is not going to have any effect, so same equation. That means we do have x-axis symmetry here for this graph. Y-axis symmetry, we will replace x by negative x, and that would also give me the same equation because when negative gets squared, it does not change anything. So that would mean yes, we do have x-axis symmetry here, y-axis symmetry here. Let's check the origin symmetry. For origin symmetry, we replace x by negative x, y by negative y. And if that doesn't change my equation, then we have x-axis symmetry and y-axis symmetry. And that means we have origin symmetry, I'm sorry. So x squared plus y to the fourth equals 5 does not change. That means we do have origin symmetry as well. Quickly reviewing, to test for symmetry, for test for x-axis symmetry, we will replace y by negative y. To test for y-axis symmetry, we will replace x by negative x. Our equations should not change. To test for origin symmetry, replace both x by negative x and y by negative y, and that should not change the equation. That means we have origin symmetry. Let's see even odd functions. Even functions are symmetric about y-axis. When you think about even functions, think about the easiest one, parabola. If you notice, parabola has two congruent parts if you fold along the y-axis. So even functions are symmetric about y-axis, and odd functions are symmetric about the origin. That means if you rotate the graph by 180 degrees, you get the original function back, or we can reflect the graph over y equals x and we can see the reflection of the graph. So symmetric about the origin, that means we can rotate the graph by 180 degrees and we'll get the same piece of the graph back. Even functions have y-axis symmetry. Here's an example of an even function, and we can see the y-axis acts like a mirror. If xy is a point on the graph, negative xy is also going to be a point on the graph. Odd functions have origin symmetry. That means if I go ahead and rotate piece of the graph by 180 degrees, my graph will remain the same. So if we rotate it by 180 degrees, we will get the same graph back by rotating 180 degrees. For an odd function, if xy is on the graph, negative x, negative y is also on the graph. Odd functions have origin symmetry, so xy is on the graph, negative x, negative y is also on the graph. The graphs that have symmetry about x-axis, they are not functions at all, so they're not really functions. They can be relations, but if x-axis acts like a mirror for a graph, it's not a function anymore. Even, odd, or neither. So let's think about the first one. We can see we do have x-axis symmetry, so that would y-axis symmetry, so that would be an even function because we have y-axis symmetry here. And then second graph looks like none. It's neither. It does not have it's not even, it's not odd because it does not have symmetry about origin, and it does not have symmetry about y-axis. The last one, we can see if we rotate the graph by 180 degrees, we would get the same thing back. So that would be symmetric about origin, and that's odd function. Even, odd, or neither checking algebraically. So if f of x is equal to f of negative x, then the function is even. That means replacing x by negative x does not change your equation, then it's an even function. And if f of negative x is equal to negative of f of x, then that would be an odd function. If written in the equation form, changing x to negative x and y to negative y gives the same equation, then that would be an odd equation or odd function, odd relation. Right, let's see an example. Decide if the given function is even, odd, or neither. So I'm going to replace x by negative x and see if that makes any difference. Looks like I have the same function back. So if I replace x by negative x, it did not really change my function. F of x is equal to f of negative x. That means this is an even function. Another example, you want to check if this graph is, or this equation is even, odd, or neither. So I'm going to go ahead and replace g of negative x, which is going to be 9 negative x to the 5th minus negative x to the 3rd. It's negative 9 x to the 5th minus, it would actually become plus x to the 3rd. Because the negative gets cubed will be negative, and the negative and negative will become positive. And if I pull out a negative out of it, I'm able to get the original function back. So we can say here that g of negative x is equal to negative of g of x. That means this is an odd function. G of negative x is negative of g of x, then that would be opposite of original function. If we replace x by negative x, that's an odd function. Another example, we want to decide if this function is even, odd, or neither. So let's go ahead and replace x by negative x. That would be negative x squared plus 2 times negative x plus 1, which is x squared minus 2x plus 1, h of negative x. Now, h of negative x is not equal to h of x, and it's also not equal to opposite of h of x. So that means this function is going to be neither. It's not even, it's not odd, it's neither. That was all for this video. We talked about symmetry about the axes, symmetry about x-axis, y-axis, and origin, and even odd and neither functions.